Alrighty, gang, we are almost there. We have one review, one practice test, final review to go. I'm here to make a video review of the review. Okay. What is a mole? How's Avogadro's number related to it? A mole is a number. It is 6.022 times 10 to the 23rd. That's what a mole is. Now, a mole of any substance, like let's say carbon, right here, 12.01 AMU per atom of carbon, but that upsizes when you use Avogadro's number so that 12.01 grams of carbon is 1 mole of carbon, but that's still 6.022 times 10 to the 23rd atoms, molecules, whatever. Okay? All right, molar masses are the easiest thing going. It is how many ever of those things you have times their molar mass all added together. So I have iron, 55.85. I have carbon, 12.01. And I have oxygen, 3 times 16. And I'm going to add those numbers together as soon as I find my calculator. 3 times 16, enter, plus 12.01 plus 55.85, that is 115.86, and the units are grams per mole. That just means that 6.022 times 10 to the 23rd of those molecules weighs 115.86 grams. All right, Al2CrO43. Okay, so this 3 has to multiply times everything inside of the parentheses. So what I have is 2 times aluminum, and aluminums are 20, I'm going to round to 27. It's 26.98. You're going to see me round a lot. On the test, you might want to round a little less than me, but 2 times 27. And then I'm going to add that to 3 chromiums. Chromiums are 52. So I have 3 times 52. And then I have 12 oxygens, so 12 times 16. And then I'm going to add all those answers together. So what I'm going to do is I'm just going to do it in parentheses here in the calculator. So I'm going to go parentheses 2 times 27, parentheses plus, parentheses 3 times 52, close parentheses, plus 12 times 16 oxygens, or 12 oxygens times 16 grams per, and that is 402 grams per mole. That is my answer. I didn't actually do the math for the individuals. I just put them in parentheses and added them all together. Hopefully nobody struggles with molar masses. All right. Convert 5.68 moles of, so first we got conversions, and then later we'll have stoich. We have no balanced equation, so we know this is not stoichiometry. So what I know is that in 5.68 moles of phosphorus atoms, for every 1 mole of phosphorus atoms, there are 6.022 times 10 to the 23rd atoms. And if I do that math, 5.68 times 6.022 times 10 to the 23rd, that is going to be 3.4 times 10 to the 24th atoms of phosphorus. Since you're not writing it out on the test, I'm not going to be a stickler for the review. I just want to see some right answers. That way I know that when you take the final exam, you are ready to rock and roll. All right, 6.2 moles of carbon dioxide into mass in grams. Okay, this is another conversion, 6.2 moles CO2, carbon dioxide. For every 1 mole of CO2, there is, let's see, some grams here. 16 plus 16, that's my 2 oxygens plus a carbon at 12.01. That is 44.01 grams. Here I didn't round as much. CO2. And 6.2 times that answer is 272 point, we're just going to round up to 0.9 grams of CO2. Don't forget your rules that diagonally, the units have to cancel, moles of CO2, and it's only units, it's not number, moles of CO2, moles of CO2. Whatever the units of my answer are going to be in the top of the last box. So if I have 3 boxes, the top of the last box will contain whatever units my answer is supposed to be in. Convert 36 grams of nitric acid into molecules. So here I'm going to need to do 2 conversions. How do I know that? Because I don't have a conversion from grams to molecules. What I know is 1 mole is 6.022 times 10 to the 23rd molecules. What I also know is 1 mole is molar mass in grams per mole. So I'm going to do 2 conversions here. I'm going to start with 36 grams of HNO3. Down here has to be grams of HNO3. By the grams rule, whenever I write grams in a box, the other side of that box has to be 1 mole of that substance, so HNO3. That means that this unit has to be moles of HNO3. And since I'm trying to go to molecules, I will go to molecules of HNO3. And I know this is 1, and I know this is 6.022 times 10 to the 23rd. What I don't know is how many grams are in HNO3. So I'm going to do 16 plus 16 plus 16 plus nitrogen is 14.01 plus a hydrogen, which is 1.01, and I get 63.02 grams. 63.02 grams. Now it's a math problem, and I'm just going to molecules of HNO3. So 36 times 6.022 times 10 to the 23rd. Hey, whenever you're using scientific notation, whenever you're using Avogadro's number, you should put it in parentheses, because your calculator is going to try and do order of operations. And so it's usually a problem when you're dividing more than when you're multiplying. But I put it in parentheses just as a matter of course. That way I never forget. Enter, and then I'm going to divide by 63.02. And I don't have to divide by 1 because you know that's just the answer. And my answer is 3.44 times 10 to the 23rd molecules of nitric acid. Okay, find the percent of chlorine and iron chloride. So it is the part divided by the whole. In this case, the part is the chlorine. So I have 3 times, and if I look on my friendly periodic table here, chlorine, right there, 35.45 grams per mole. So 3 times 35.45, enter. So I have 106.35 on top. And then I'm going to add a iron to that, plus, clear, plus 55.85, that gives me 162.2. And if I divide 106.35 divided by that answer times 100, don't forget the times 100, I find that it is 65.6% chlorine. It's the part divided by the whole, but you got to remember the whole includes everything. So if you have water and a salt, it includes both. If you want to know the percent mass, it is the percent of the salt over the percent of or over the mass of the entirety of the entire solution. All right, give empirical formulas. So you're basically just factoring out the greatest common factor. So here I can factor out a 2 and I get C4H9. And it has to be a common factor to both subscripts. So if there's not a common factor, then there's nothing you can do about it. So C4H9 is done. That's as far as I can go. There's no common factor between those two. C2H6O2, I can factor a 2 out. That gives me CH3O. Remember, empirical is just some number smaller. This is twice as small. This is twice as small. This one's going to be twice as small. NO2. Factor a 2 out. Divide 4 by 2, it's 2. Divide 2 by 2, it's 1. Same thing throughout all of these, right? Okay. All right, so they want an empirical formula for acetic acid. So I have a series of steps. Step 1, percent to mass. Remember, that requires magic. Hecto. All right, don't look yet. Don't look. Wait, wait, wait. Just keep turning your head. Wait, 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 wait. There. Voila! I am a magician. I have turned them into grams. Now I know that if I divide by grams, that gives me the moles of substance. So like if I just took this half of this formula right here, 36 divided by the molar mass gives me moles, the units of my answer. So if I divide this by 12.01 and I divide this by 1.01 and I divide this by 16, I'm going to get moles of carbon, moles of hydrogen, and moles of oxygen. So it is percent to grams, grams to moles, divide by lowest. That's my next step. So 40 divided by 12.01 is 3.33. And don't round too much on this step. 6.71 divided by 1.01 is 6.64. I think you can see where we're going with this. And 53.29 divided by 16 is 3.33. If I divide by the lowest mole total, which is 3.33, I get 1, 2, 1. That means that my carbon is 1, so I don't need to write anything. My hydrogen I have 2 of, and my oxygen I have 1 of. They could do another step. They could give me a molar mass and ask me what the empirical is. They've done that in number 9 here. So if this is the molecular mass, the molar mass, it's going to be some number bigger, like twice as big or 3 times as big or 5 times as big as my empirical. All I have to do is take my empirical formula and turn it into a mass. Carbons are 12, hydrogens are 1.01, and there are 2 of them, 2.02, and oxygen is 16. If I add all of that together, it's 12.01. Let me not cheat here. 30.03. So 30.03 grams per mole for my empirical formula. If I divide my molecular formula by my empirical formula, 92.09, they've used an imperfect number here, but that's okay. I get 3. Remember, tenths of a percent, I can ignore those things. So what I know is my molecular formula is 3 times as big as my empirical formula. That means 3 times as many of all these atoms. That means C3, H2 times 3 is H6, and O1 times 3 is O3. That is my molecular formula. All right, page 1 in the books. Let us keep going. All right. Mole ratios, love it. All mole ratios are coefficients. So 2, 2, and 3. KClO is 2. O2 is 3. So that is a 2, 3. The only thing they're testing there is your ability to get these things in the right order. Don't put 3, 2, because that is not the mole ratio for this stuff. It is 2, 3. Boing. Okay. O2 to KCl. So there are 3 O2s for every 2 KCl. So 3, 2. That is the mole ratio. Okay, now we're into the stoich. We made it to stoich. So now we have to have the proper number of boxes. If I'm going from moles to moles, it's 1 box. If I'm going from moles to grams or grams to moles, it's 2 boxes. And if I'm going from grams to grams, it is 3 boxes. And how do I know I'm looking at stoichiometry and not just a conversion? There has to be a balanced equation with it. And so if you give me a balanced equation, I know I'm into stoichiometry territory. So how many moles of lithium chloride can be produced from 4.5 moles of gold chloride? So 4.5 moles of AuCl3. And this is a 1 boxer because I'm going from moles of AuCl3. This is the heart of the conversion. Remember, you're going to have moles of one thing over moles of the other thing, always. Moles of LiCl, and that means my answer is going to be in moles LiCl. And I know that this ratio is 1 mole of AuCl3 for every 3 moles of LiCl. So it is literally 4.5 times 3, which is 13.5 moles. How many grams of gold can be produced from 2.75 moles of lithium? Well, now I'm going to grams of gold, so I know I'm going to need 2 boxes. Remember all my rules. Diagonally, my units must be the same for them to cancel. And the units of the last box in the top are the units of my answer. So I'm looking for grams of gold. That means this is going to be grams of gold. By grams rule, the gram rule, I have 1 mole of gold here. Not AG. Tried to make that silver on you. Trying to convert gold to silver. And then by the diagonal rule, I know that this has to be moles of gold. But that's as far as I can go backwards. So now I'm going to go forwards. I'm going to go, I have 2.75 moles of lithium. That means this is moles of lithium. Now I have all my boxes complete. Moles of lithium canceled by moles of lithium. Moles of gold canceled by moles of gold. Grams of gold, my last units of my answer. And if I look on the periodic table for gold, I will see that there is 197 grams for every 1 mole of gold. And if I look at the balanced reaction, I will see that there are 3 moles of lithium right there for every 1 mole of gold right there. And now it is a math problem. 2.75 times 197, enter, divided by 3, enter. 180.58 grams. 180.58 grams. That is my answer, 180.58. And then the last one's going to be grams to grams, of course. How many grams of gold chloride are needed to produce 143 grams of lithium chloride? So you notice I don't care what the words say. I'm just looking at the number and what I need to get to. The number is 143 grams of lithium chloride. I don't care if it says produces or uses or anything because it doesn't matter to me. And then I know there's going to be 3 boxes here because I'm going to convert grams to moles, moles to other moles, and then moles back to grams of grams AuCl3. And then should I work backwards or forwards? Let's work forwards. So I have 143 grams of lithium chloride. That means this is going to be grams of lithium chloride. By grams rule, anytime I write grams in a box, the other side, the top of that box, or in this case, on the other side, the bottom of that box, is going to be 1 mole of that stuff. That's the only thing we know the mass of is 1 mole of that stuff. So this must be moles of LiCl. And that's as far as I can go forward. I don't have a rule for what goes above moles. That doesn't exist. What I do have is this. The units of my answer are the top box, AuCl3. And I have grams rule. Whenever I write grams in the bottom of that box, I write 1 mole of that substance. And then diagonally, the rules have to be, the units have to be the same. So this is moles of AuCl3. And now I need to do some math here because I need to add these things up. So I have a lithium at 6.9 plus a chlorine at 35.45. That gives me 42.35 grams here. Okay, and then this is the heart of the conversion, the heart of the problem, where I have moles of one thing over moles of the other. We know that comes directly from the balanced reaction. So I have 1 mole of AuCl3 for every 3 moles of LiCl. And then I need the mass of AuCl3. So 35.45 times 3. I have 3 of those plus a gold at 197 is 303.35 grams of gold chloride. Now it's math. It's literally 143 times 1 times 1 times 303.35. Enter. Divided by 42.35. Enter. You notice I hit enter after every time. Divided by 3. Enter. That is 341.43 grams. And I know I got that right because y'all already did that one in front of me. What is the difference between dissociation and solvation? Okay. Solvation happens in everything that dissolves. whether it's covalent or ionic. So solvation equals it dissolves. But salts do an extra step, don't they? Like covalent stuff dissolves, but it still stays sugar molecules because they are covalently bonded. So if I have like a C6H12O6, a sugar, a type of sugar, that doesn't fall apart in water. It dissolves, the molecules will separate from each other. If I have a bunch of molecules of sugar, they will all separate from each other, but that is not dissociation. Dissociation is when my salt is dissolving. After it dissolves, after kind of the formula units fall apart, then you have what's called dissociation. And that's where water molecules surround your ions. So I have a cation and I have an anion. And this is what happens to ionic compounds. There is a complete transfer of an electron. Do not forget. And that means the negative end of water, which is the oxygen end, which I draw as the bigger bubble. They do that in AP Chem. And then the hydrogens are the smaller atoms than oxygen, so they're attracted to the cation because they're the anion because they are positively charged. This is an anion, that's cation. Remember, cats are positive. So the waters surround the ions and they allow them to separate. That is dissociation. Dissociation. My spelling brain is put away for the year. Yeah, so that is dissociation. Everything dissolves or everything solvates that dissolves. Solvation just means dissolves. Ionic stuff though does the extra step and does the dissociation. So that's more interesting. And this also lets electricity flow through it. It's called an electrolyte. So we can flow more electricity through salt water than through regular distilled water. All right, 3 factors that affect rate of solvation of a solid and a liquid. You know them as shake, bake, and break, but you know it is agitate, surface area, and temp. I can increase the temp, I can increase the surface area, I can increase the agitation. All of those things will affect the rate at which something dissolves. Sugar by the spoonful is going to dissolve quicker than a sugar cube. Identify all the ways that I can increase the rate of solvation for a solid in a liquid. Well, I can agitate, I can increase surface area, I can increase temp, I can increase agitation. All of those things, I guess it's looking for that you are increasing all of those things to increase the rate, as opposed to just factors that affect the rate. What factors affect the rate of solvation of a gas in a liquid? That's simple. It is temp and pressure. And remember, the temp is opposite of a solid. If you want a solid to dissolve, you use a high temp. If you want a gas to dissolve, you use a low temp. That's why a ice cold Coke maintains its carbonation, and a hot Coke will go flat very quickly. Yum, 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 yum. How many liters of 1.25 molar HCl solution would you make if you used 85 grams of HCl? So what I need is this right here. I need the molarity formula. Molarity equals moles over liters. Since I know molarity equals moles over liters of solution, and I know the molarity, it's 1.25 molar, and I know the moles, I just have to change them into it, but 85 grams of HCl divided by 1.01 is a hydrogen plus 35.45 is a chlorine. That's 36.46 grams per mole. If I do that division, 85 divided by that answer, I get 2.33 moles. And I can say 2.33 moles on top and X liters of solution on bottom. and now it's a solvable problem. Remember that if your x is on bottom, whatever is over here just trades places with it. So it is literally 2.33 divided by 1.25 equals 1.864. X equals 1.864 liters of solution. That is my answer. Again, I'm going to use the molarity formula. What is the molarity of 0.75 liters? That is on the bottom. Made with 210 grams of KNO3. Well, it looks like I have another converting into moles job here. 210 grams of KNO3 divided by, let's see, I have 3 oxygens. That's 16 plus 16 plus 16. I have 1 nitrogen plus 14.01, and I have 1 potassium, which is 39.1. That is 101.11 grams, 101.11 grams per mole for KNO3. And if I do that math, 210 divided by second answer, I get 2.08 moles. 2.08 moles. And now it's moles over liters, so I can do this math. 2.08 divided by 0.75. That is a 2.77 molar KNO3 solution. I can't help myself. I always have to make it a proper label. Proper label has this, the molarity symbol, and whatever it is, the molarity of that the concentration, and whatever that stuff is. All righty, where are we at? Ooh, we're at 30 minutes. All right, so I'm going to end this video because downloading videos longer than 30 minutes are problematic. And then I'm going to start recording again for part 2 on page, I guess, what are we at? 3? We're on page 3 now? Yeah, we're on page 3.